Solving systems by substitution. Let's take a look at this example where we're solving a system of equations graphically. Remember, to solve a system of equations graphically, we want to take the two equations in our system and graph the lines that represent the equation and find where those lines intersect. So we have our two equations here. We have y equals x plus 6.1 and y equals negative 2x minus 1.4. So the first equation, y equals x plus 6.1, would have a y-intercept of 6.1. So we have to go to 6.1 on our graph, which we can tell where 6 is on our graph, so maybe we'll go a little bit above that to represent 6.1. And then our slope is 1 from the coefficient of 1. So 1 over 1 tells us from 6.1 to go up 1, right 1. So it's a little, again, tricky because we've got 6.1, so going up 1 would be to 7.1. And then over 1, and then 8.1 over 1, and 9.1 over 1, up 1 over 1, up 1 over 1. Hopefully we're doing this okay. At this point we're estimating. Or we can go down 1, left 1, down 1, left 1. And again, at this point we're estimating where that 0.1 above unit is to get our first line. Okay. And then the second line, y equals negative 2x minus 1.4, that's in slope-intercept form as well. We have y in both of these equations. We're very easy to see the y-intercept and the slope. So y equals negative 1.4. So that's our y-intercept. And then our slope is negative 2, or negative 2 over 1. So our y-intercept is negative 1.4. So that means go down 1 and then somewhere a little bit in between negative 1 and negative 2, but maybe a little bit closer to negative 1, maybe somewhere about there. And now we'll use our slope of negative 2 over 1 to go down 2, right 1. So again, you have to be careful when you're going down 2 from negative 1.4. So maybe down 1, down 2, right 1, maybe about there. Go down 1, 2, right 1, maybe about there. 1, 2, right 1. Or we can go up 2, right 1. Again, we're being approximate. Up 2, right 1. Up 2, right 1. Up 2, right 1 to get that second line. So the solution would be the point of intersection, which we can visually see is going to be this point here. But at this time, we're going to have to, well, what is that point, right? It's, let's see, negative 2, maybe negative 2 point something. We're not exactly sure, negative 2 point something. And we can go up 1, 2, 3, 4 point something. So maybe it's negative 2.5, comma, 1, 2, 3, 3 point, was it 4 or 3? 3, I think, maybe 3.8. It's almost 4, but we're not really sure. This system is turning out to be really difficult to find the solution by graphing. So take a moment and think about it. Why is it so difficult to find this solution? Why was it difficult to solve this system by graphing? Look at the equations we're given. Think about the challenges that we've had, right? One of the major things is that our y-intercepts are decimals. We're not using the units on the graph, and the intersection was then a decimal. It wasn't a nice intersection between the units on the graph. They're decimal solutions. We're estimating all over the place. So this system is not the best for graphing. We need a different method to solve this system so we can get an exact solution. We want the exact decimals, the exact answer to this system. We don't want to have to estimate. There has to be another way. Graphing can be inefficient or approximate when solving a system of equations. But another way to solve a system of linear equations is to use something called substitution. Substitution allows you to create a one-variable equation when you originally had two equations with two different variables. There are 3 steps to solving a system using substitution. But instead of looking at them all at once, let's actually go through an example and break each step down and go through what exactly it means and how it helps us find the solution to a system without graphing. The example we're going to use is actually the example we were trying to graph, but we were having such difficulties because of the decimals with the y-intercepts. But let's show that using substitution can get us an exact answer. So the directions read to solve the system using substitution. So the first step when using substitution is that if you are not given a variable already alone, we want to find the easiest variable to solve for in one of the equations, meaning get a variable alone in one of our equations. Well, if we look at our system here, both equations actually have the variable y alone. So step number 1 is already completed for this system with no work needed. We have the variable y alone in actually both equations. So step number 2 is actually the part about the word substitution. Step number 2 says we're going to substitute the expression, and it's really of your choice because remember now we have 2 for this system, but we're going to substitute the expression of your choice into the other equation and solve for that variable. So we are going to randomly pick the first equation and the fact that y equals x plus 6.1. We're going to take the expression that y equals that x plus 6.1 and put it substitute it in for y into the other equation, into the equation y equals negative 2x minus 1.4. It's going to substitute in that variable. This will actually let us write a brand new equation separate from the other two. It's almost like we're combining the other two equations, but we're actually substituting in that variable y. So you won't see the variable y in our new equation. That variable is gone. It's at home sick. And in is the substitute, that expression from the first equation, x plus 6.1. And then it still equals the rest of the equation, negative 2x minus 1.4. We've substituted the first equation into the second equation to actually have a brand new equation where we don't have the variable y. We only have one variable x. We have x plus 6.1 equals negative 2x minus 1.4. We now have an equation with only one variable. So the rest of step 2 is to solve for that variable. So we need to solve for x. So in the equation, x plus 6.1 equals negative 2x minus 1.4. First, we'll add 2x to both sides. That will give us 3x plus 6.1 equals negative 1.4. We'll then subtract 6.1 from both sides, and that will leave us with 3x equals negative 7.5. Then we'll divide both sides by 3, finally giving us that x equals negative 2.5. So this is the value of x for our solution with that new equation we created through substitution. So we found the value of x in our system's solution. Now we need to find y, because remember, your solution isn't just one variable, it's both variables. So step number 3 in substitution is to substitute the solution you found, in this case it's x equals negative 2.5, into either equation and solve for the other variable, in this case y. So if we substitute it into the first equation, y equals x plus 6.1, that will give us y equals negative 2.5 plus 6.1, which gives us y equals 3.6. If we chose to substitute it into the other equation, y equals negative 2x minus 1.4, we would get y equals negative 2 times negative 2.5 minus 1.4, which is 5 minus 1.4, which will still give us y equals 3.6. So the solution to the system of linear equations is now the ordered pair x comma y, which we've now discovered with our values is negative 2.5 comma 3.6. And just to reiterate, we only had to plug the x value into one of the equations to get this answer. The second one just provides a check. If it comes out the same, our solution must be correct. Now, another good habit or good practice is to check your solution after you found both the x and y values, right? After you evaluate the solution, it's good practice to double check your work by substituting the solution into both equations and making sure you get a true statement for both equations. Remember, if it's a solution to the system, it should make both equations in the system true when you substitute in those values for x and y. In this case, we want to see if x equals negative 2.5 and y equals 3.6. We want to make sure those equations are true. So if we substitute them into the first equation, we end up with a true statement of 3.6 equals 3.6. And if we substitute them into the other second equation, we end up with 3.6 equals 3.6. So our checks end in true statements, so that is our solution. Negative 2.5, comma 3.6. And we use substitution to find it instead of graphing. Let's see another example where we're solving a system using this new method of substitution. Now we have the system 3x minus 2y equals negative 1 and y equals x plus 1. Remember, step number 1 is that if you are not given a variable already alone, we want to find the easiest variable to solve for, meaning getting it alone. But since one equation, the second equation of y equals x plus 1, is already solved for y, step number 1 is already completed. We don't have to do any work. We can move on to step number 2, which is using the substitution. It says to substitute the expression into the other equation. So again, we'll use the equation that is already solved for y equals x plus 1, and we'll substitute the expression for y for what it equals into the other equation. So we're taking the expression from that second equation, x plus 1. We're taking what y equals, and we're substituting it into the other equation where y was. So instead of 3x minus 2y, the new equation will not have the variable y in it. We're substituting in y. Y is gone. Y is homesick. You will not see the variable y anymore. Instead, you'll see the equation with the new expression. We'll have 3x minus 2 now, not y, but x plus 1, that expression, and then still equals, and we have negative 1. So now we can continue with step 2 and solve for that variable. So we have our equation 3x minus 2 times the quantity of x plus 1 equals negative 1. If we distribute the negative 2, we'll get 3x minus 2x minus 2 equals negative 1. Combining our like terms, 3x minus 2x is x, and then adding 2 to both sides, we'll get that x equals 1. So we've solved for half of our solution. Step number 3 gets us the other half. We have to substitute that solution into either equation and solve. Now again, we're going to do both equations just to show you get the same answer. If we substitute an x equals 1 into the first equation, we get that y equals 2. And if we substitute it into the second equation, we also get that y equals 2. Either way, we end up with the solution of 1, 2. Finally, it's good practice to check to see if 1, 2 satisfies both equations. If x equals 1 and y equals 2, you should get true statements if you substitute them into both equations. And as you can see, if you substitute 1 and 2 into the first equation, you get negative 1 equals negative 1, a true statement. If you substitute it into the second equation, you get 2 equals 2, another true statement. So since the ordered pair satisfies both equations, we have our solution to the system. We have 1, 2. So when solving using substitution, remember your 3 steps, and then it's good practice to check your solution. And we have this method that we can find solutions to systems without graphing.